Is it full screen now?
Yes, now
All
it's
right.
full screen.
All right.
Perfect.
Great. So, yeah, IronDict, transparent dictionaries from polynomial commitment schemes. So I want to start a talk by illustration of a simple scenario in secure messaging. Imagine Jon Snow has Ygritte's mobile phone and Jon Snow wants to text her in WhatsApp. So what Jon Snow needs first to do is request public key of Ygritte from WhatsApp server. But the server might be faulty, and in that case, it may actually return public key of someone else, like Joffrey. And here, Jon Snow has no way of knowing that it's not actually public, it's not actually texting the right person, and essentially Joffrey will be impersonating Ygritte without Jon Snow ever realizing it, and it might end up in some awkward situations for Jon Snow. And this is where the transparency comes into play. So the whole goal of transparency is that everyone gets the same view of the server state. And it means that since server has to reply back consistently with its state, it means that the responses are going to be consistent for everyone. For example, the way it actually solves the problem I mentioned in the previous slide. So Ygritte can check her public keys correct on the WhatsApp server, and since Ygritte and Jon Snow have the same view of the server, and server will essentially respond back the same for their queries, then when Jon Snow queries Ygritte's public key, he's gonna get the right public key this time when you have transparency. And in a high level, the transparency model looks something like this. So we have the server and clients as before, but now we have two extra roles, the public bulletin boards and the auditors. And in a high level, what happens is that the server publishes a commitment to its state or a summary of its actions on the bulletin board, and auditors observing the public bulletin board will audit the server actions. And if the server is being faulty, if they find that the server is being faulty, they have some whistleblowing procedure that would let other people know that the server is being faulty, which might have legal or reputational consequences for the server. All right, transparent dictionaries, the abstract model we want to work with. In a high level, a transparent dictionary, you can think of it as a dynamic dictionary mapping a set of labels to a set of values, where like the dictionary can have different states in different epochs. And what I mean by epoch is discrete points in time. For example, you may have epochs every hour, every day, something like that. And it's a generic concept which has like different applications in different settings. For example, the two different applications of transparent dictionary are public key directories and software distribution. So in the case of the public key directory, the dictionary would be essentially a mapping from the usernames to the public keys. For example, in the case of WhatsApp, it would be a mapping from the mobile phones to the people's public keys. And it has been actually deployed by Keybase and WhatsApp, and apparently iMessage and Signal also uh, wanna deploy this as well. And the other application, software distribution. So in this case, the dictionary would be a mapping from software versions to the hash of the software. So when you wanna, essentially, when you wanna make sure that you have the right software, given the software version, you look up the dictionary and downloading the hash, you know, uh, if you have downloaded the right software, and it's been deployed by the Linux Foundation. But the important application for this talk and the paper for us is the public key directory. Essentially, the challenging application is the public key directory. Because working with public key directories, we have dictionaries which are larger than other applications. For example, they can be as large as 2 billion, which are the WhatsApp user size reported back in 2020. And also, we need high scalability. For example, we require a throughput of at least 200 updates per second, according to the WhatsApp people. And we also have like some requirements which may not be necessary for other settings. For example, in the setting of a public key directory, we require privacy, which might not be necessary for software distribution. I will actually illustrate privacy in the future slides. But for now, what is the high recipe of building a transparent dictionary? So at every epoch, what the server does is that it publishes a commitment to the dictionary on the bulletin board plus some invariance proof. And what this invariance proof is that it basically proves some invariance hold between consecutive states of the dictionary. I will illustrate it in a couple of slides, but for now, just know that like at every epoch, essentially the server publishes a commitment to the dictionary plus some invariance proof. And what are the expected functionalities from a transparent dictionary? So the most natural functionality we probably guess is the lookup operation, where like you wanna look up value corresponding to some label in a state of the dictionary. For example, Jon Snow might be interested in getting Ygritte's latest public key. But the second functionality, which may not be like super intuitive, is proof of consistency. And what proof of consistency says is like it basically proves that value corresponding to some label has not changed from some epoch I to epoch J. It means that in all of those intermediate epochs, the value has been consistent. For example, Jon Snow might be interested in a proof that his public key hasn't changed since last year. But you may ask, like, why is Jon Snow interested in that? So, for example, why does Jon Snow want to know his public key hasn't changed from epoch I to epoch J? Well, consider this scenario. Assume that Jon Snow has been beyond the wall with no internet connection from state I plus 1 to state J minus 1. It means that Jon Snow is online in state I, and then he's going to be offline until state J, and then he's going to come back online in state J. And the way that the server can cheat here is that, which we call the ghost key attack. So the server can, when Jon Snow is offline, essentially can change Jon Snow's public key in the dictionary and serve a different public key to the users, which is essentially impersonating Jon Snow. And later, before Jon Snow coming back online, he would essentially revert the public key back to the original. And when Jon Snow comes back online in state J, he would never realize that he was being impersonated. And that's why we essentially need the proof of consistency to make sure that the public key hasn't changed between epoch I to epoch J. Alright, next I want to say like what are the different solutions we have to value consistency. Actually, we're not going to use any of these approaches, but it's still good to know them. So the most naive approach would be probably the naively looking up all the states. So if you want to make sure that your value hasn't changed from state I to state J, you basically look up your value in state I plus 1, all the way to state J, and basically check that all of these values are equal. But you're gonna have like a linear number of proofs, and for example, assuming you're offline for 3 months, and there's gonna be like epochs, I don't know, every 10-15 minutes, you're essentially gonna have like check so many proofs. We basically don't want that for poor Jon Snow. Now another solution in previous work is version invariant. So in this scenario, the server sets a version for each value in the dictionary, where like initially the version for each value is going to be 0 when added to the dictionary. Now each time a value is updated, essentially the version is incremented by 1, and the server promises to increment the versions only if and only if the value changes. So that is like a promise from the server. And assuming we have version invariant correctly, now if you want to make sure that your value hasn't changed from epoch I to epoch J, all you need to do is like at epoch I, you basically look up your value and version, and then later in epoch J, you again look up the value and the version, and you just basically check that the versions are equal. Because if the server has, for example, changed your key in between, it means at least the version should be incremented by 1, so they cannot be equal. So that's really cool. By only doing 2 lookups, we can do the proof of consistency. But I said the server promises to increment the versions. How do we make sure that the server actually keeps the promise? And this is where the proof of invariance comes into play. So if you remember, I said like at every epoch, the server publishes a proof of invariance plus the commitment to the dictionary. And this is essentially what the proof of invariance would do here for us. So in the case of the value versions, the proof of invariance simply proves that versions are incremented only for the change values. For example, if you consider this very simple dictionary with like 3 people, since only the public key of the first row has changed, only the version of the first row should be incremented. And the proof of invariance here would uh, basically prove that only the version for the first row has been incremented. Alright, so far I have said like what a transparent dictionary is, what application it has, and we know like it has like cool applications in practice, and we know like what functionalities we want from a transparent dictionary. But what are the research questions here? So going back to this diagram, I mentioned that like auditors are the one observing the public bulletin board, and if the server is being faulty, essentially they're gonna find out about it and tell everyone else. But the question is like, who are these auditors here? And as it turns out, these are not everyday users in the previous schemes. So basically, the question of like who the auditors are can be answered by the question what computational power we expect from the auditors. And the computational power of the auditors goes down to the proof of invariance. So for example, if you have large proof of invariance, it means that auditors have to do a lot of computation. But if you have small proof of invariance, it means that less computation is expected from the auditors. And as it turns out, the audit proofs for the Merkle trees, which are the baseline for essentially all the existing deployments of transparent dictionaries, are huge. Uh, Basically, because like Merkle opening proofs cannot be batched, the proof sizes are going to be linear in the number of updates. And reported by the WhatsApp people in a talk in Real World Crypto 2 years ago, so the proof of invariance for WhatsApp is like 200 megabytes every 5 minutes, which gives like a throughput of 200 updates per second. And as you see, like 200 megabytes every 5 minutes is not feasible for everyday users to be downloading it and checking it. And so the solution here is like, we trust some non-profit companies doing the auditing on our behalf. So one solution you might think about is like, okay, you have some big proof. Why couldn't you just like use it on use a snark and make a sync proof for it? Uh, and it's like people have tried to do it. We had this work hackathon. So hackathon is like a distributed snark which runs on a cluster of 4,000 machines. And so our main motivation in hackathon was doing the updates for a transparent dictionary in a sync way, but we ended up being getting like a very low throughput of 10 updates per second. And primarily the reason is like standard hash functions like SHA are very expensive to be expressed in the circuit, so that didn't work out. Now the question here is like, can we make auditing cheap enough so everyday users like me with a mobile phone, I can do the audit myself and I don't have to trust some non-profit companies doing it for me? Uh, the other motivation is like Merkle trees do not give perfect privacy. So first of all, privacy is crucial when the transparent dictionary is used in the context of secure messaging, because something like the pattern of changing keys, which might not be, I don't know, important in software distribution, is very important in this setting, because if the adversary knows some user doesn't change their key regularly, it may make them a potential target for them. And the observation here is that tree constructions do not give us perfect privacy. In a high level, the way they define privacy is they define some leak function which is inherent from the construction, and they say like we only leak this amount of information. For example, in the case of Seamless, the leak function is for the lookup operation is that each lookup reveals the last time that the key was updated. So the other question here we have is, can we get a transparent dictionary with perfect privacy? And yes, the question is affirmative, and that's going to be IronDict. So our goal in IronDict is, so we don't want to have high server costs because we want our scheme to be really practical for WhatsApp. We're trying to get rid of the high auditing costs. We want to make like auditing so cheap that people on their mobile phones can be doing it. We essentially want to get rid of the uh, non-profit companies doing it on our behalf. And finally, we want to get rid of the leakage function. So we want to have perfect privacy. We don't want to be really leaking anything. Any questions so far? All right. So I'm gonna get into the scheme, IronDict. So our contributions. Our first contribution is like we give a generic construction of transparent dictionary based on any polynomial commitment scheme, uh, which is like generic. So you can essentially initiate it with like different schemes getting different concrete costs. We're the first scheme ever to have perfect privacy. We do have support of efficient of fast forwarding. So our fast forwarding scheme with IVC is 1,000 times better than Versa, which is the previous state of the art. I will explain when we get to the slide of fast forwarding what fast forwarding is if you don't know about it. And finally, our scheme is really practical if you want to use it, for example, for WhatsApp. So we have implemented our scheme for a dictionary of size 2 billion, which was the reported number of WhatsApp users back in 2020. Our scheme is like self-auditing. The audit proof is around 10 kilobytes, which can be verified very fast on a everyday laptop. We have efficient lookup and proof of consistency both for the server and client, and we do have a support of like 10,000 updates per second, which is like much more than we need in practice. And finally, we have low memory and computation for the overhead. So the overall summary of the last bullet point is that this is practical for WhatsApp. But before getting into the technical details, I just want to point out two technical terms I'm going to be using if you're not familiar with them. So one of them is like a multilinear polynomial. A multilinear polynomial is a multivariate polynomial where the degree of each variable is at most 1. For example, if you consider this polynomial f defined over three variables x1, x2, and x3, uh, it's essentially a summation of some terms where like in each term the degree of each xi is at most 1. And one fact I'm going to be implicitly using in the talk, and we implicitly use it in the paper, I think, is that evaluations of the polynomial over the Boolean hypercube essentially give us a representation of the polynomial. And when we want to work with a polynomial, we essentially consider its evaluations over the Boolean hypercube. Alright, the second term I want to use is a polynomial commitment scheme. So a polynomial commitment scheme is, before saying like what it is, I just want to point out it's like the backbone of snarks. So over the 15 last years, there's been like so much research on it. It's a standard primitive. And in a high level, what a PCS allows us to do is like it allows us to commit to some polynomial and later prove its evaluation at some point without revealing the whole polynomial. And it has some cool properties. For example, it is succinct, meaning that the commitment size given to the verifier is much smaller than the original size of the polynomial. It is efficient, saying like the verifier time is sublinear in the polynomial size. And finally, it's binding, saying the prover cannot change the polynomial once it commits to it. Alright, getting into the core of the paper. So the first thing I want to say is like how we can model dictionaries from multilinear polynomials. So consider a very specific type of dictionary, where the labels here are points in the Boolean hypercube of size n, and values are non-zero field elements. We see there is like a very clean one-to-one mapping from this very specific type of dictionary to multilinear polynomials, where like we use so I said like a multilinear polynomial can be represented by its evaluations on the Boolean hypercube. Now the way we do this mapping is like for each li, we assume that the polynomial at li is evaluated to vi, and for the rest of the Boolean hypercube, it's evaluated to 0. And we see essentially we have a very clean one-to-one mapping from that very specific type of dictionaries to multilinear polynomial space. But that type of dictionary is not interesting for us in practice. So the dictionaries that we are actually interested in are dictionaries where the labels and values are arbitrary strings of zeros and ones. So next I'm going to explain like how we can go from that very specific type of dictionary to the general dictionaries with arbitrary strings in domain and range. So the first observation here is that if you have a hash function h, which is collision resistant in one way, as long it essentially gives us a one-to-one mapping from arbitrary strings to the non-zero field elements, as long as size of our field is large enough. And for example, it's like more than 2 to the 128. We need it to be large enough so you cannot do birthday attacks. And using this one-to-one mapping from arbitrary strings to non-zero field elements, we see that a dictionary, you can essentially replace the range of the previous dictionary, which was non-zero field elements, with arbitrary strings of zeros and ones. So now we have a dictionary from points on the Boolean hypercube to arbitrary strings. But we're not there yet. We still have the points, we still have our domain to be points on the Boolean hypercube, but we want it to be arbitrary strings. And we see the same strategy doesn't work for the points on the Boolean hypercube. So if you want to do it similarly, you define a hash function from arbitrary strings to the points on the Boolean hypercube. It's not going to be one-to-one this time because, for example, if you're working with a dictionary of size 2 billion, our Boolean size, our Boolean hypercube size will be more or less 2 billion. It means that it's not large enough, and if you use a hash function, at the end you're gonna get some collisions. So we cannot apply the same strategy here, and we do it differently actually. So the way we do it is like we keep two different polynomials to model the general dictionary. So assume this time we have two dictionaries, index and value, where the dictionary index takes arbitrary strings and takes them to points on the Boolean hypercube, and the value dictionary, which takes points on the Boolean hypercube and takes them to arbitrary strings. And now you see that the composition of the index dictionary and the value dictionary gives us a general dictionary from arbitrary strings to arbitrary strings. And we know that each of index and value, we can model them with a multilinear polynomial. And that means like with two multilinear polynomials, we can model the general dictionary. So that is our first step. Yeah, like each dictionary state would consist of two subdictionaries. And now if you have some label L that you want to find its corresponding value, what you have to do is like you first look up the index dictionary for label L, and you get some index Y, which is going to be some point in the Boolean hypercube. And then you open the value polynomial at point Y, and you get the corresponding value for label L. So what are like the expectations from these dictionaries? So the index dictionary, which is going to be a mapping from the labels to the assigned indexes, we want it to be append only. For the purpose of this talk, I'm not going to get into the details of the being append only, but essentially you're going to translate the append only constraint to a zero check, and then you translate the zero check into some sum check and polynomial evaluation. But for the purpose of this talk, I'm not going to get into these details. And the value dictionary, which maps the indexes to the values, we don't really have any constraints on it because the values in the dictionary may change. So this dictionary allows changes for its values too. But one small detail I want to mention about the index dictionary is that how are we going to assign indices to labels? So if you remember, I said you cannot basically use one hash evaluation because our Boolean hypercube is not large enough, so we're going to get collisions with a high probability. And so we're going to use the technique of open addressing. What the technique of open addressing in a high level, we iteratively compute some hash function giving us some points in our data structure until we finally find a vacant spot. So it looks like something like this. So you have a hash function h, fancy h, and you start with 0, you append 0 to the label, you hash it, you get some point in the Boolean hypercube. Now if you see if it is vacant, you assign it to the label. But if it's not vacant, you increment 0 by 1, and then do the same procedure again and again until you find some vacant spot. But one important detail here is that we require size over provisioning. And what it means is like we need the capacity of the dictionary or our data structure to be more than the expected number of elements we have. And this is very common when you use open addressing in data structures. You always set the capacity to something larger than the expected number of elements, because like if the capacity is almost equal to the expected number of elements, as you get closer and closer to that capacity, you're gonna be needing like more hashes until you find some vacant spot. But here, for example, if we set the over provisioning to 4x, on average we only need to open like 1.3 points on the Boolean hypercube to find some empty spot, which works in our case. And the value dictionary, as I mentioned, we don't really have any constraints on the value dictionary, so the server can update it as it wishes. But the value dictionary is important in the proof of consistency. Just to remind you, proof of consistency is when you want to prove that value corresponding to some label hasn't changed from some epoch I to epoch j. So what is the high level of our consistency check? The high level is that we define some polynomial delta, some difference polynomial delta, which is going to be the difference of two consecutive value polynomials. And now we see that the value polynomial as at n, where like n is larger than m, can be written as the value polynomial at m plus a summation of the difference polynomials, which is the first equation you see on the screen. And the observation here is that the value polynomial at m and n are equal at some point x, and if a ghost key attack has taken place, it means that like the server has changed the value in between and reverted back. It means that these different polynomials are not going to be 0, and they have cancelled out each other, so their summation was 0. And our high level idea is like we use randomness so the difference polynomials cannot cancel out each other. And yeah, so we define these polynomials rand polynomials, where like rand n is defined as the initial values plus some linear random combination of the difference polynomials. And the very key observation here is if the rand polynomial n at y is equal to the rand polynomial m at y, then with a very high probability, all the value polynomials from like value polynomial n minus 1, all the way to value polynomial at epoch m, all of them are going to be equal at point y. And we essentially reduce the proof of the consistency proof from checking like n minus 1 equalities to only checking one single equality between two polynomials using randomness. And if you're curious where the randomness comes from, we derive it from the Fiat-Shamir heuristic, and that's why our security model is in the random oracle. So our dictionary will look something like this. Now we have the previously we only had the index and value dictionary, but now we also have another rand dictionary. Just to remind you, the index dictionary was a mapping from usernames to points on the Boolean hypercube. The value dictionary will be a mapping from points on the Boolean hypercube to the public keys. And the rand polynomial will be a mapping from points on the Boolean hypercube to a random linear combination of values, which we use for proof of consistency. I just have a couple of points left. So privacy in the transparent dictionary. Our privacy is like very simple. So the way we do it is like we see that like what types of uh, so what really server publishes when you like query from the server, what really server returns back. We see that the only information that the server publishes are like subject proofs, polynomial commitments, and openings. If you don't know what a subject proof is, just think of it as something that you can essentially make it zero knowledge very cheaply. Uh, and polynomial commitment and opening, we can also make them like zero knowledge cheaply as well. So if we make all of these primitives zero knowledge, it means that the server with every functionality, it only reveals what it's supposed to, not nothing more than that, and that is the definition of zero knowledge. And by making all of these zero knowledge, we make the whole system zero knowledge, which is very simple. And finally, the concrete instantiation. So I mentioned IronDict is uh, generic over any polynomial commitment scheme. But the question is like which one to choose. So which one we want to concretely use for the construction. So we initiate our system with KZH. Why we wanted to go with KZH? Well, KZH has some good features. So it has a sublinear opening time. It supports efficient zero knowledge transformation, which we need for the privacy, and also KZH has a constant commitment size, and we care about the commitment size because that's going to be published on the bulletin board. And yeah, we also like its authors, so we were a bit biased as well. That's why we went with KZH. And we have implemented our system. So for a dictionary of 2 billion users, we have done a comparison with WhatsApp. And we are the first work in academia that we have actually done benchmarking for more than 10 million keys. So comparing IronDict when initiated with KZH4 with WhatsApp, which is based on seamless plus parakeet. So our lookup proof and verification is almost around 20 kilobytes, which can be verified like in 25 milliseconds, while for WhatsApp is like 2 to 4 kilobytes, but that can be verified much faster because we use pairing and WhatsApp uses hashes and CPUs are like more optimized for hashes. Our lookup time for the server is like 200 milliseconds, but for WhatsApp is like 6 milliseconds, and primarily that's because like uh, lookup proofs for Merkle trees are pre-computed. But 200 is not really that bad as well because it's just a read-only operation. When you really want to design it, the lookup operation only requires a read-only access to the database, so it's not that bad. And we get a throughput of like a lot, like 10,000 or something. But WhatsApp only has a, well, they require a throughput of like 200. That's why they essentially set the throughput to something like 200. And our audit proof and verification is like 10 kilobytes, which can be verified in like 15 milliseconds. But the audit proof size of WhatsApp is like 200 megabytes, which can be verified in 2 seconds. And just like a couple of things to mention, so our audit proof and verification, the first row and the last row, can be made like 7 or 8 times better if we use KZH8 instead of KZH4 without really meaningfully changing the server costs. And yeah, we're also like looking into the lookup time for the server, the 200 milliseconds. We believe we can make it better, but that's ongoing work. Uh, and finally, I just want to quickly mention what fast forwarding is. So assume you're an auditor and you have been offline for 1,000 epochs, and now you come back online. It means like you have to check 1,000 invariance proofs. So what a fast forwarding allows you to do is it sort of like, batches the proofs, so allows you to check less number of proofs instead of 1,000. And there are mainly like two approaches for fast forwarding, and we have both approaches in our work. So the first one is based on IVC, and we estimate that our IVC is 1,000 times better than Versa. First of all, because like our circuit is like 100 times smaller than Versa, and also we can, for some technical reasons, we can initiate our scheme with elliptic curves, which are like 10 times more efficient than the elliptic curve which was used by Versa. So overall, we're like 1,000 times better. It means like our fast forwarding is like really practical. Um, and finally, there's this other approach, the checkpoints, which reduces a linear number of proofs to a logarithmic number of them, which can be seen as a lightweight version of IVC. And we also support that one as well. Um, and yeah, thank you.
Thanks.
That was a fast one.
Does anybody have questions?
I guess I had a question about the open addressing. I guess you just didn't mess up any of the proofs. I guess you just prove for all the locations that it didn't change.
Sorry, could you say that again?
No, just when you want to test for non-membership with open addressing, I guess you have to set a maximum number of hashes that you could do, and then it fails, and then you just prove for everything up to that.